Hello. Sometimes researchers or data analysts need to compare the mean of a group with a specific value. For instance, when a teacher wants to know if the scores of a group of students are above a cutoff level and overall the class meets the criteria for mastery. In this case, the teacher can move on with instruction, otherwise some reteaching might be needed. In such situations, a one sample t-test may come in very handy. In this presentation, I will describe different types of t-tests and explain the hypothesis testing process involved in a one-sample t-test, beginning with stating the hypothesis, stating the significance level, calculating the t-statistic, and interpreting the results. There are three main types of t-tests. The independent samples t-test, which compares the means of two different groups. The paired samples t-test, comparing the means from the same group at different times. And the one sample t-test, comparing the sample mean to a known value. A one sample t-test compares the mean of a single group to a known value or a theoretical expectation. This test is used to determine if the mean of the sample is significantly different from a specific value. For instance, comparing the average test score of a class to the national average test score. An independent samples t-test compares the means of two independent groups to determine if there is a statistically significant difference between them. This test is useful when researchers want to compare two different groups, such as students taught using two different instructional methods. The assumptions for this test are that the samples are independent, the data are approximately normally distributed, and the variances of the two groups are equal. A paired samples t-test, also known as a dependent samples t-test, compares the means of two related groups or the same group at different times. This test is appropriate when the same subjects are measured under two different conditions or at two different times. For instance, measuring the improvement in student performance before and after an educational intervention. This test relies on the assumption that the differences between the paired observations are normally distributed. The one-sample t-test is a statistical test used to determine whether the mean of a single sample is significantly different from a known or hypothesized value. The hypothesized value is often the population mean, but it can also be a numerical value such as a cutoff value. Using a t-test for this purpose, rather than a z-test, is appropriate when the population standard deviation is unknown and when the sample size is smaller or the data have a symmetrical distribution, but the distribution is not perfectly normal. In the field of education, researchers and practitioners often rely on the one sample t-test to evaluate the effectiveness of new teaching methods, interventions, or curricular changes. For instance, an educator might use a one sample t-test to compare the average test scores of a particular class to a national benchmark or a historical average. This comparison helps to determine whether a new instructional approach is effective in improving student performance. There are several steps involved in a one sample t-test. The first one is to state the null and the alternative hypotheses. The null hypothesis is that x bar, or the sample mean, is equal to a given value, which can be the population mean. The alternative hypothesis represents the opposite of the null hypothesis. If the alternative hypothesis is one-sided, HA is that x bar is smaller or larger than the given value. If the alternative hypothesis is two-sided, we say that x bar is different than the given value. For instance, consider a scenario where a teacher wants to determine if his student's average score on an assessment differs from the average population score of 85. The teacher can formulate the following null hypothesis. The average class score is equal to 85. Or he can say that the difference between the class average and the population average of 85 is 0. If the teacher has reasons to believe that his student's average score should be higher than the population average, for instance, if he teaches gifted students, the alternative hypothesis can be one-sided. He can state this one-sided alternative hypothesis as the class average score is significantly higher than 85, or the difference between the average class score and the population average of 85 is significantly greater than 0. If the teacher does not have a specific reason to believe that the average class score might be higher or lower than the population average and simply wants to know if there is a significant difference, the alternative hypothesis is two-sided. He can state his two-sided alternative hypothesis as the class average score is significantly different from 85, or the difference between the average class score and the population average of 85 is significantly different from 0. In practice, we select either a two-sided or a one-sided alternative hypothesis. And we do this at the beginning of the study before we even conduct the statistical analysis. However, in this presentation, I will demonstrate both the one-sided and the two-sided tests to explain the differences. The significance level, noted as alpha, is a crucial concept in hypothesis testing, including with the one-sample t-test. It represents the probability of rejecting the null hypothesis when it is in fact true, or the type 1 error. Therefore, the significance level is a predetermined threshold set by the researcher before conducting the statistical analysis. Common values for alpha are 0.05, 0.01, and even 0.10. For example, if alpha is set at 0.05, it means that there is a 5% risk of concluding that a difference exists when in fact there is no difference. The significance level can be explained and represented graphically using the t-distribution curve. The entire area under the t-distribution adds up to 1, representing 100% probability, or all the possible outcomes, where values closer to the mean have higher probability of occurrence, and the probability of occurrence decreases as the distance from the mean increases. As illustrated in these images, the significance level alpha is located under the tails of the t-distribution, representing the more extreme values with lower probabilities of occurrence. When the t-test is two-sided, alpha is divided in two and is located at both ends of the distribution. When the test is one-sided, alpha is located at one end of the distribution, for instance, under the right tail, as indicated in the image on the right. Using the t-distribution, the significance level determines the critical regions and the critical values for the test statistic. For a one-tailed test with alpha at 0.05, the critical region is the area in one tail of the t-distribution that has the extreme 5% of the total probability. For a two-tailed test with alpha at 0.05, the critical region is split between the two tails with 2.5% in each tail. The t-critical value, noted as TCV, represents the value of the t-statistic where the significance level alpha begins. This value can be obtained from the table of the t-distribution critical values using the degrees of freedom and the one-sided or two-sided level of confidence. For instance, when alpha is 0.05 and we have 24 degrees of freedom, a two-sided t-test has the critical values of 2.064, and alpha is divided in half and placed at the two ends of the t-distribution. At the same level of confidence and the same degrees of freedom, a one-sided t-test has the critical value of 1.711. The next step is to calculate the t-test statistic. A t-test statistic in a one-sample t-test is a measure used to determine whether the mean of a single sample differs significantly from a known or a hypothesized value. This statistic follows a t-distribution with n-1 degrees of freedom, where n represents the sample size. It is calculated by taking the difference between the sample mean and the given value, which can be the population mean, and then dividing this difference by the standard error of the sample mean, as indicated in this formula. For instance, the teacher in our example wants to compare the mean score of her students to the population mean of 85. She collected data from a sample of 25 students. The group of students has a mean score of 90 with a standard deviation of 10. Therefore, the value of the t-statistic can be calculated using this formula, and we obtain the value 2.5. The value of the t-statistic can be calculated manually using this formula, or using online calculators or statistical software. The advantage of using online calculators or statistical software is the increased precision and the opportunity to obtain more detailed results. But most importantly, statistical software and online calculators can also calculate a probability for the t-statistic, which is called a p-value. This probability represents the chance or the probability to obtain this value when the null hypothesis is true. The p-value of the test statistic varies based on the directionality of the test. In our example, the probability of the test statistic is approximately 0.01 or 1% for a one-sided test and 0.02 or 2% if the test is two-sided. These results indicate that if the null hypothesis is true, which means if mu is equal to 85, there is only a 1% chance of obtaining a sample mean of 90 with a one-sided alternative hypothesis, and a 2% chance of obtaining a sample mean of 90 when the alternative hypothesis is two-sided. Graphically, the p-value represents the areas under the tails on the outside of the t-statistic. For a one-sided test, the p-value is located on one side of the curve. If the test is two-sided, the p-value is at both sides of the t-distribution. The images in this slide illustrate the location of the t-statistic and the p-value in a one-sided test versus a two-sided test. After calculating the t-statistic, the next step is to compare the t-statistic to the t-critical value, or to compare the p-value to the significance level alpha. We do not need to do both. Both procedures lead to the same result. In the absence of statistical software or online calculators, we can use critical values. Otherwise, we most often use p-values. In our example, the value of the t-statistic was 2.5 with a one-sided p-value of 0.01 and a two-sided p-value of 0.02. For the one-sided test, the t-critical value is 1.711 and the test statistic, which is 2.5, is larger than the critical value. Using the p-value, we can see that our p-value of 0.01 is smaller than alpha of 0.05. For the two-sided test, the t-critical value is 2.064, and the test statistic is again further from the mean than the critical value. Additionally, the p-value of 0.02 is smaller than alpha of 0.05. After examining t-statistics and p-values in relation to critical values and the significance level, data analysts decide whether to reject or retain the null hypothesis. If the t-statistic is further from the mean than the t-critical value, the null hypothesis is rejected and the alternative hypothesis is accepted. However, if the t-statistic does not exceed the critical value, the null hypothesis is retained and the alternative hypothesis is rejected. Alternatively, if we use the p-value, we can compare the p-value to the significance level alpha. If the p-value is smaller than alpha, the null hypothesis is rejected and the alternative is accepted. If the p-value is larger than alpha, the null hypothesis is retained and the alternative is rejected. In this presentation, I describe different types of t-tests and explain the hypothesis testing process involved in a one-sample t-test, beginning with stating the hypothesis, setting the significance level, calculating the t-statistic, and interpreting the results. I hope that the explanations provided were helpful.